Hello everyone, welcome back to our YouTube channel. In this video, I am going to discuss about hysteresis curve, magnetocrystalline anisotropy, and crystal structure of magnets and how these crystal structure affect the magnetic properties. So let's get started. In last class, I explained you all about magnetic properties, all about magnets, all basic concepts and basic terminology of magnets. In this video, I'm going to discuss hysteresis curve in brief. To understand hysteresis curve, first I need to give you an overview about these properties. First one is magnetic field, which is represented by H. It is external magnetic field. Second one is flux. It is magnetic flux, which is B dot A, where B is total magnetic field, which is the combination of internal plus external magnetic field. By the way, I have explained all these properties in last class in detail, so you can watch that video as well. Third one is magnetization, which is represented by amps. So magnetization comes due to orientation or movement of magnetic dipole in a particular direction. So whenever a material magnetic moment or magnetic dipole align themselves into a particular direction, at that time they create a magnetic field. So that magnetic field is called as magnetization. Okay, saturation magnetization is maximum value of magnetization, and these two terms are very important, which is retentivity and coercivity. So retentivity is nothing but the residual magnetization which is present inside the material after removal of H, and coercivity is nothing but resistance to demagnetization. So how our material is resisting the demagnetization. So that is given by coercivity. So these two are very important, and among them, coercivity is what we need in our material. So further, I will explain you more about it. So first, let's get started with hysteresis curve. For example, we have a material, okay, and in this material we are passing current. In this coil we are passing a current I, and this is coil which is completely surrounded by on this material. So we are passing current, AC current inside this. Okay, so as we know, a current carrying conductor produces magnetic field around it. Similarly, this conductor which has a current, it produces a magnetic field around it. That magnetic field is known as H, external magnetic field. Okay, and this magnetic field is changing. As we know, the current is positive, this H will also be positive, and if the current goes negative, this H will also go negative. So this magnetic field is changing. So on x-axis, we have this H, which is changing, so positive H or you can say negative H. On y-axis we have B. B is combination of internal plus external magnetic field, as I told you earlier. So now when we pass the magnetic field, when we pass the current, it has the magnetic field, and because of this magnetic field, this dipole start arranging themselves in the direction of magnetic field. So when we increase the value of H, the value of B increase in this way, and it reach a maximum value which is known as saturation. And when we decrease the value of H, when we move to the negative cycle, this magnetic field decreases. So it decreases like this. It cuts its own axis at a point. This point is known as retentivity. And when it decreases further, it cuts the x-axis at a point. That point is known as coercivity. And further, this plot achieves the saturation maximum magnetization, and again it increases like this. So this is hysteresis curve. So this curve tells us the dependency of B on H. So how our B is depending on H is given by this curve. So this curve is known as hysteresis curve. So in this curve, there are three important points. First one is R, which is retentivity. Third one is coercivity, and second one is coercivity. Third one is modulus of B and H, which is BH max. So these three terms are very important. So in this slide, I explained you we are passing a current through a conductor, and because of this current, we are having a time varying, what I can say, changing magnetic field. We are passing time varying current, and because of that, we are having a changing magnetic field. And because of this magnetic field, dipoles are arranging themselves in a particular direction, and we are getting this plot. And this plot is known as hysteresis curve. So yes, this one is better picture of hysteresis curve. So this curve tells the dependency of H and B, how our B is dependent on H, and this curve actually look like this. So this one is saturation magnetization, maximum value of magnetization. So, or you can say maximum value of B, which is flux density or magnetic flux density. Further, this one is retentivity and this one is coercivity. So these 2 points and the BH max, these three terms are very important. So coercivity, as I told you, it's resistance to demagnetization, and retentivity is how much magnetization is retained by the material when we remove this edge. When we remove the edge, how much magnetization is present inside the material, that is given by retentivity. So let's get further. This one is magnetization. So this is the plot between B versus M versus H, and this is the plot which is B versus H. So like it's a combination. It's a combination of both BM and H. So, as I told you earlier, M is nothing but internal magnetic field, B internal. So, this is coming due to the orientation of magnetic dipoles, and B is the combination of both, Bi plus Be. So, this plot M versus H is more wider than B versus H. So, you have to remember this thing. More wider means high coercivity, high coercivity. Okay, and they have high coercivity and they have same retentivity. So you can see retentivity is same. So this red curve is M versus H and this blue curve is B versus H. So in B versus H, coercivity is less. Why? Because we are considering both the factor, internal and external. If we are considering external factor, then coercivity is definitely going to be less. Why? Because external magnetic field can demagnetize the material, but the internal magnetic field is completely internal. It depends on the magnetic dipole. So as we are incorporating both the terms Bi and Be in B, that's why the coercivity is very less, but we are not incorporating B external in case of magnetization, in case of M versus H plot. Because of that, coercivity is higher in that case. So in this case, coercivity is higher. In this case, coercivity is less. As you can see in this plot, this blue plot. In this plot, coercivity is less. In this plot, coercivity is high, and this plot is wider. And that is what we want in our material. We want our material should have more coercivity so that it will be a magnet for a long time. It will not demagnetize. Coercivity is nothing but resistant to demagnetization. If our resistance to demagnetization is very high, it means it will retain its magnetization for a long time. And that is what we want in our magnetic material. So these two plots are also very important. Further, yeah, this one is the third term which I was talking. First one is R, which I explained you, retentivity. Second one is C, coercivity, and third one is BH max. So BH max is what we get maximum energy product in second quadrant. So we measure this term after the retention, or you can say once the value of H becomes zero, after that we measure this term, BH max. So this term is measured in this case. Let me erase all these things. Yeah, in this case, in this second quadrant, after the removal of H. So this is H. Okay. When we come back here, H becomes zero again. After this, we measure pH max. So in second quadrant. So more the value of pH max, more the value of pH max, higher is the strength, higher is the magnetic strength, because this curve will gets more sharper because the value of B and H is increasing. Okay, so it will become more sharper. So the coercivity will increase, retentivity will also increase, and magnet become very strong. So BH max should be maximum, not maximum. You can say it should be optimum. So these are the three terms which are very important. So this is retentivity, which is represented by BR in that plot. Remanence, where H becomes zero, correct, on y-axis, and this is coercivity, which is Hc, where B becomes 0 and it is on x-axis. Okay, so these two terms are important. So let me explain you these three terms again in a short. So retentivity, coercivity, and DH max. Okay, retentivity is nothing but how much magnetization is retained when we remove the external magnetic field. Okay, so that is nothing but retentivity. Here it is. And coercivity is resistance to deformation. No, not deformation, sorry. It is the resistance to demagnetization. Sorry for that. Resistance to demagnetization. Magnetization. And BH max, as I told you, it is measured in second quadrant after the removal of magnetic field, after the removal of H external or external magnetic field, it is measured in this quadrant, second quadrant. And higher the BH max or sharper the curve, if this region, let me show you that region. Yeah, if this region, this complete region is sharp, then the magnet is very strong. We can say this complete region, this blue line. If this region is sharp, our magnet is very strong. So that is nothing but BH max. BH max. Okay, and it is mod. So it will always be in positive. So we are taking mod. This one is mod. So these three terms are very important. Further, we have magnetocrystalline anisotropy. It is nothing but an energy, or we can say it is a barrier. It is a barrier which we have to cross to magnetize our material. So better I can say it's our our external magnetic field, which is represented by H, should be higher than this energy. This is nothing but an energy. So it's as I told you, it's a barrier. So this one is barrier. So if we want to go from point one to point two, we have to cover this barrier. So this barrier is nothing but MCA, magnetocrystalline anisotropy. So if we want to magnetize our material, our H value should be higher than this, higher than this. So then only we can cover this barrier. Then only we can overcome this barrier. So our external magnetic field must be higher than MCA to magnetize the material. So MCA is nothing but it's a barrier, or you can say it refers to the energy which is required to magnetize the material. So if our external energy is greater than MCA, then we can magnetize the material easily. Okay, so this is nothing but MCA, magnetocrystalline anisotropy. And further, so there are two axes in a crystal, for example, BCC and FCC. So in FCC, there are two axes. In all the crystal, there are two axes. First one is easy axis, second one is hard axis. So easy axis and hard axis. So along this easy axis, MCA is very less. So your barrier in the case of easy axis is very less. So it's very less. But in case of hard axis, it is very high. So you have to give a lot of energy in case of hard axis. So there are two axes, easy and hard. Along easy, MCA is very less. Along hard axis, MCA is very high. So these two things are very also very important. You should remember these two things. So in FCC, easy axis is this one, from this point to this one, which is uh, which is one, one, and one. So one, one, one. So this is easy axis, and these are eight in FCC. So this one is one. Similarly, one crystal is present on this side, right? This side, this side. So two. Similarly, there are three, four, five, six. So like there are eight. One, two, three, four, five, six, seven, eight, like this. So eight are there. In case of FCC, the easy axis is this one, zero, zero. This one is easy axis. So if you magnetize your material along this axis, it becomes very easy. So H value, we don't have to give a lot of H. We don't have to give a high value of current. Okay, so it's become easy to magnetize the material along this axis, along easy axis. So you have to remember that thing. But what happens if you magnetize the material along easy axis? It will magnetize quickly, but it will demagnetize quickly as well. So that is what we don't want. We want our material to magnetize quickly, but it should not demagnetize quickly because we want our material to sustain its magnetization for a long time. So that is what we want in our material. So that's the issue of, you can say, easy access. So in these two crystal structure, BCC and FCC, easy access are too much. So that's why we magnetize the material along easy axis and they form soft magnets because we are magnetizing them along easy axis. So they magnetize quickly, but they will demagnetize quickly as well. So these magnets are called as soft magnets. While in case of tetragonal and SCP, here you will have very less few easy direction. So they are very hard to magnetize. So they will magnetize not quickly, but they will magnetize, but they will take time. They will need high external magnetic field. Okay, but they will not demagnetize quickly, and that is what we want. They will sustain their magnetization for a long time. So their coercivity will be very high as compared to soft magnet or as compared to the FCC or BCC crystal. So because they will resist the demagnetization. So if you take FCC and BCC, these two crystal structure are symmetric, not too much symmetric, but they are symmetric. They are higher symmetry. They have good symmetry as compared to these two. So if any material or any crystal structure is symmetric, it means it has low anisotropy. So the direction or property along the direction or different property in different direction, that is nothing but anisotropy. So if the material is highly symmetric, so it is lower anisotropic, and lower anisotropic has many directions. So we can magnetize it quickly. Yeah, so I was discussing about tetragonal and SCP crystal structure. So let me simplify this concept for you. So in FCC, material is symmetric, right? Symmetric, and because of that, it has low anisotropy, lower, or you can say lower anisotropy. Okay, and because of that, it has like so many easy access. So material will magnetize with lesser H. Okay, so because MCA will be very less, magnetocrystalline anisotropy is very less, so it will magnetize with less H value, but it will demagnetize quickly. So these material forms soft, or these materials with these crystal structure, with FC crystal structure, they will form soft magnets. But the material like tetragonal crystal structure, the material having tetragonal or SCP, these material they have very less symmetry. So they are higher anisotropic. And as they are higher anisotropic, they will magnetize with higher H value because their MCA will be very high. But they will not demagnetize quickly. They will not demagnetize quickly. Their coercivity will be very high. And that is what we want to make hard magnets. Hard magnets. So crystal structure plays very important role for for creating the magnets. So this is what I was explaining on this slide, and this is some points I have written here. To magnetize the material, the magnetic dipole inside are initially pointing in a random direction. So for example, this is our material, and this is green boundaries, and these are dipoles. So they are oriented in a random direction. So to align them in a direction of an external magnetic field, you have to rotate or move these dipoles. So for example, I have applied an external magnetic field. We have to move them, we have to rotate them in a particular direction, in the direction of H, like this, like this. So, but because of MCA, magnetocrystalline anisotropy, some direction are easy and some are hard. So as I told you, on easy axis, MCA is very less. On hard axis, MCA is very high. Therefore, you must supply energy to overcome material's internal resistance. So the material internal resistance is nothing but MCA. So as I told you earlier, we have to overcome this energy to magnetize the material. So these energy aligns the dipoles properly along the external magnetic field. Higher the anisotropy, more energy needed to magnetize, but it will demagnetize after a long time. So its coercivity will be very. So we prefer to magnetize the material along hard axis because it increases its coercivity, and that is what we want for making hard magnets. So these three terms or these three topics I have explained you in this lecture, whether it's hysteresis curve. Second one was magnetocrystal anisotropy, and third one is crystal structure. What is the importance of crystal structure for making a magnet? So thank you for watching. Stay tuned. See you in the next video. Thank you.